Welcome back, everybody. Today, what we're going to do is continue diving into networks and specifically put a bow on a few of the Internet Protocol pieces. We lean on the Peterson and Davey Computer Networks and Systems Approach book, which you can find online, book.systemsapproach.org. So let's start off with addressing. So we've talked about IP addresses. We've talked about how they are 32 bits long, a word size long. In general, you can think of that as 32 bits. And those bits are a series of ones and zeros. Now, we often see IPv4 addresses as four numbers dotted together. So you can see here an IP address like 128.96.34.15. You know what? I'll blow this up a little bit. Although it moved everything around on me. Here we go. And so this first, any of these numbers are a number between 0 and 255 because they represent 8 bits, and we're translating those 8 bits back into a decimal number. So you're always going to see numbers between 0 and 255 for a valid IPv4 address, and you'll see them in this form. So this host 1 has an IP address that is 128.96.34.15. This one cool thing about how addresses have typically been given out is they're given out in blocks, and I'm not going to talk about the class full system of how they used to give out these blocks. Instead, I really want to focus in on how they're kind of used today, and largely they're used with subnets. And when you look at R1, it's broken into two sub networks, right? There's a network that's kind of above it here, and there's a network that's kind of below it here. All of the IP addresses on this network above are grouped together, and they're grouped together because they have similar bits. So for example, any host that's sitting on this network up here is going to start with 128.96.34. Now, there's even more to it, and the more to it is that every address is going to end with a number between 0 and 127. And the reason for that is because the subnet mask here is 255, 255.128. And so what that looks like is a series of ones followed by a single one and a series of zeros. So this subnet mask is 24 ones and 8 zeros, but this particular subnet mask that ends in .128 has a 1 in this bit, right? We're translating that 128 into bits. And so what that means is all of the numbers for this subnet, all of these bits are the same for any host on this network. And this is why when you're in a subnet or a network and you're like, hey, what's your IP and what's your IP? That's why their IP addresses are similar, is because they're in the same subnets. Now, modern masks tend to be just a number of bits rather than the classless mask is kind of like, well, the same 24 bits are the same, or the same 25 bits are the same. It still resolves into a subnet mask that is a number like this, but really it helps to think of them as ones and zeros. So these ones all say everything in this subnet all have to match kind of the same first set of numbers. And then everything on the bottom has to have the same set of numbers. Now, they both have the same subnet mask, 255.255.255.128. But what's different here is that the subnet number, the thing that is similar, is different. So in this one, the subnet number is a 0. And in this one, the subnet number is a 128. And basically what we're saying is all of the numbers that are the same in these, they all start with 128.96.34. But the ones on the bottom of R1 down here on this blue line, they're all going to have the final number be between, say, 128 and 255, whereas all the ones on this blue line are going to be 0 to 255. And I can tell that from the subnet number. And so any address that I get, I can run the mask over, and if it matches, I know it's on the same subnet. And if it doesn't, then I know it belongs to a different subnet. And so routers can use this to kind of figure out whether they need to do, to figure out which interface to push things over, and figure out what they kind of might need to do kind of at a lower level. So you can see here, like if host 3, well, let's look at the routing table. That might be helpful too. So if you think of one of the hosts, you know that if you're in host R1 here, and you get something that's for this particular subnet with this subnet mask, that you need to push it out over the top interface, and maybe that's interface 0. You know that if it's in that second blue line, you need to push it out over its bottom interface, and that's interface 1. And you know that if it's for this other subnet down here, that it needs to go to router number 2, which is then going to figure out what it's supposed to do with it. And it will have a different subnet mask and a different subnet number down there that describes its network. And so this is an example of subnetting. Subnetting can be really, really useful to help you think about how your forwarding table looks, and to help you kind of organize your networks in different ways. It's super useful. And I think we couldn't get away without talking about these. If you look at any sort of IP setup, you're going to see subnet masks, subnet numbers, and maybe gateway numbers too. For example, this router has an IP address here, which tells H1 kind of like who it is communicating with. And that kind of is a natural segue into our next segment, which is ARP. So let's switch over here and talk about ARP a little bit. I guess with the increase in font, everything is kind of moved around here. So what is ARP? ARP stands for Address Translation. It is basically the way that we figure out how the IP address and the MAC address are related. So ARP actually stands for Address Resolution Protocol. And the short answer is, if I go back to this picture here, I think this picture is really useful. If I'm trying to figure out, like, host 1 is trying to talk to, let's say, some other host on the same network, it doesn't necessarily need to go through the router. But if it is sending some message out, the router needs to know that this host exists and what its IP address is, and to relate that IP address with a MAC address. Now, because we're operating on the link layer, once we get the information, we have to push that out through direct links, right? And we've talked about how direct links communicate, and they communicate through MAC addresses. But the internet communicates through IP addresses. So if host 3 is sending this information through, and R1 gets it at the internet level, the network layer, it has the IP address and everything, and it wants to communicate it to host 1, it could just drop this off into this network as a broadcast, but that would get really, really messy. So instead, it's going to interact with whatever its link layer protocol is to hand things over to H1. And so in general, that is, it's going to target kind of this H1 directly by its MAC address. And ARP is the process by which R1 learns what this IP MAC address pair is. And so there is a mechanism in Ethernet, for example, where H1 will say, hey, everybody on the network, I'm going to send a broadcast message. This is my MAC address. This is my IP address. I'm looking for where I'm supposed to send stuff. And R1 will get that message, and it will record that IP and MAC address, right? And then it will send a message back directly to H1 and say, I've got you. I'm your gateway. This is my MAC address that you want to send things over if you're trying to drop things out over the internet. And so ARP is kind of the protocol that you would use in order to make that happen. Sometimes IP addresses and MAC addresses change. Maybe your Ethernet card breaks and you replace it. But ARP is kind of the way that we kind of make those associations. So you can kind of see the source and target addresses and protocols and the protocol addresses and stuff like that tucked in here, because it's possible that this link is connecting to something other than the internet protocol. But this in general is meant to kind of help us map IP addresses to MAC addresses. And it is the glue that kind of ties our network layer back down to our link layer in this way. Let's talk about DHCP for a second. When I was a young lass, again, changing the font size just really screwed up the scroll here. When I was a young lass and I wanted to say, connect my machine to the internet, I had to contact the administrator and ask them what my IP address was, because every port on the Ethernet was mapped directly to an Ethernet address. And so that was actually kind of really tight as far as security goes, like a good thing, because it meant you couldn't just plug in and use the internet. Like, you had to actually configure your stuff to match exactly what the hardware says it was supposed to be. Now, for a giant network and for our idea of plug and play that we're kind of used to, where you just open your Mac and you connect to a Wi-Fi network, like, that breaks down. And very quickly, things switch over to kind of a DHCP sort of system. And DHCP can be configured in a couple ways. One is you can still map those ports to IP addresses, which I guess probably already existed when I was a young lass. That's probably what I was actually using. But nowadays, the way we use them is DHCP has a bank of IP addresses. And when you send this request for an IP address, DHCP will respond and say, hey, MAC address, I see you. here's the IP address you should use. It's registered for you for, say, a day. That's called a lease. So you lease this IP address for a while, and you have to continually like re-ask for the lease as time goes on. And what this is great for is that machines can come on and come off of the network, and the DHCP just gives you an address, and you're still limited by kind of a number of connection points. Maybe if you're plugging into Ethernet, you're limited certainly by the number of Ethernet ports that are there. Although I guess you could hub and do some interesting things that way, right? Although your network administrators are not going to appreciate that if, say, you were to do that at your school or something. But anyway, you're kind of limited still by kind of the limits of what addresses you can get and whatnot. But DHCP will handle that for you. So if you haven't heard of DHCP before, this is your moment. The last thing that I want to do, the last piece of glue that I want to talk about, again, my scrolling that up really changed things, is ICMP. So if you remember very early on, we talked about traceroute and how we got information back about the hops along your path, right? So you do a traceroute to 8.8.8.8, and it told you what your hops were to get to Google. Well, ICMP is really how it's doing that. ICMP stands for Internet Control Message Protocol. I think I got all those right. And the general idea is if a router does have to drop a packet, and it might have to do that for many reasons, then it has a methodology to respond to that. It has a way to kind of send a message saying, hey, this host doesn't actually exist on my network, or hey, I had to drop this because my traffic is too heavy, or whatever. And so when you do these trace routes, you set your TTL low, and then that router will drop that packet, and then it can send a response back like, hey, your TTL died and I had to like do this. That's one way that you could get some information back from ICMP. But it's important to know that ICMP is kind of the way that our trace route and pings are working. And some routers and some administrators can decide not to send those responses back out or to forward ICMP packets. But it makes it really horrible for debugging those networks, right? It's really challenging. Okay, well, those are the things we wanted to talk about. We talked about classless addressing and subnetting just a little bit. We talked about address resolution protocol just a little bit, where we figure out how to connect MAC addresses and IP addresses. We talked about DHCP, which is basically how you get your IP address. I don't think we described what DHCP stands for. It's Dynamic Host Configuration Protocol. So the idea is you dynamically get an IP address. And then we talked about ICMP, which is kind of how the internet sends errors back when things fail. All right, so this is some glue kind of tying up the end of the internet protocol. Hope you got something out of this. I'll talk to you guys next time. Take care of yourselves. Take care of each other. Bye.